Hey everyone, so in this segment video, I'm going to be talking about aromatic substitution reactions. We weren't able to cover this during the semester, so I'm going to have this all on video. I'll have this probably broken up into several videos. So this is the first of maybe I would say 3 or 4. So let's just get going on this. We did talk about aromaticity before. This is somewhat related to it. We're going to be seeing how we can do reactions with aromatic compounds. Okay. See if I can. Okay, there we go. So we've already seen that aromatic compounds are less reactive than typical double bonds. Let me switch to the laser pointer here. A second. There we go. So if you remember alkene reactions with Br2, alkenes will definitely react with Br2, right? Because you guys know the alkene is nucleophilic, the Br2 is electrophilic, and you're going to get an addition product of the Brs anti to each other, right? This is just a review reaction. You guys know this will happen with a regular alkene, with a regular double bond, right? But when the double bond is part of an aromatic system and you expose it with Br2, you're not going to get an addition product, right? Why is that? Because you've now lost aromaticity from adding Br2, right? And there's no reason to basically give up the cost of aromaticity and then get a product that's not aromatic. That's not a really good idea, right? The fact that the aromatic compound is so stable is going to prevent the Br2 from performing an addition reaction. Okay? So, let's see if I can go to the next slide now. If you expose an aromatic compound with a little bit of iron, though, right, which is kind of weird. We haven't seen Br2 with a metal like iron. But if you introduce iron, something interesting happens where you, instead of getting an addition reaction, you get a substitution reaction. And how is this a substitution reaction? Well, if you can see at this position, we now have a Br. Let me change this back to pen. We have a Br here, right? And before that, there was a hydrogen there at the same position. Right? So what did we just do? We substituted a hydrogen, a proton, for a Br. Okay, that's why it's a substitution reaction. And you're probably wondering, well, how the heck is this happening? This class of reactions where you have substitution reactions on aromatic rings is called electrophilic aromatic substitution. That's the name of this reaction. It's also termed EAS. Go back to my laser pointer. It's also termed EAS. So we're going to be using the words EAS, electrophilic aromatic substitution, a lot. The technical definition of it, I just mentioned it, but here's a formal definition, is a reaction in which one of the aromatic protons, right over here, is replaced by an electrophile, which is Br2, and the aromatic ring is preserved. Right? So notice that we didn't lose aromaticity in this process. We did a substitution reaction, but we didn't lose any aromaticity, which is great. All right, so let's see how this works. Well, before we see how it works, just to keep in mind that there are classes of reactions other than adding a Br. You can add other things through electrophilic aromatic substitution, EAS. You can add a chlorine, an NO2, SO3H, an alkyl group, an acyl group. We're going to talk about all of these reactions in this video, okay? So they basically go through the same process. They're all substitution reactions, right? They're all replacing a, let me go back to my pen. They're all replacing this proton, this hydrogen, with any one of these groups, right? So there's a ton of these different reactions. We're going to talk about each one of them, but they're all classes of electrophilic aromatic substitution reactions. Right? Notice I said that the Br is an example of, you know, an electrophile, but what is the nucleophile? The ring acts as a nucleophile. Okay, and notice in every single case that aromaticity is preserved. So let's dive a little more into how Br2 is actually being able to substitute a proton on an aromatic ring. Realize that it's not going to just do it alone, right? If you take Br2 and you throw an aromatic ring with it, you guys saw that it's not going to do anything. We need to add some sort of iron to it, right? Some sort of metal. And that metal is going to form a Lewis acid, okay? So before we get into Lewis acids and how it's involved in the reaction, just remember that in brominating a regular alkene, the Br2 functions as an electrophile, right? We saw this. But unfortunately, Br2 is not electrophilic enough to react with aromatic compounds like benzene. It's just not powerful enough of an electrophile. So to amp it up, to make it more electrophilic, we need a Lewis acid catalyst. Because what the Lewis acid catalyst is going to do is it's going to enhance the electrophilicity of the bromine. It's going to make Br2 a better electrophile. And you're probably wondering how that's going to happen. We saw that when you throw a metal like iron in here, okay, you were going to actually get that substitution reaction. But realize that iron is not the Lewis acid. It's when iron is mixed with Br2, when they're in the same flask, they form a Lewis acid, and in this case it's iron tribromide, FeBr3. And if you're wondering where does FeBr3 come from, let's just go back to the pen here. If I take Fe, iron, and I mix it with Br2, and Br2 is a liquid at room temperature, I'm going to make FeBr3. Okay? Which is, I believe, as a solid. Now, this equation isn't balanced, right? So to balance this, you need 2 Fe's, you need 3 Br2s, and then you're going to get 2 FeBr3s. This is kind of like Gen Chem 1, where we're just balancing a chemical equation. What I'm really just showing here is where do you get the Lewis acid? The Lewis acid is FeBr3, okay? And we make it from iron and Br2, right? So as you saw earlier, when we threw iron in the reaction, we were able to substitute a proton on a benzene for a Br, right? And this is where you get the Lewis acid. This is how you can make it, okay? Now, why is it that a Lewis acid actually enhances the electrophilicity? Right? How does it do that? How is it making Br2 more electrophilic? It's doing it like this. So you got Br2 and then FeBr3, which I showed on the previous slide how you make FeBr3. Basically what's happening is you have a lone pair of electrons on Br attack Fe, right? The iron and FeBr3. And you guys remember what the definition of a Lewis acid is, right? A Lewis acid, let me just write this out. A Lewis acid is an electron acceptor, right? And if this is your Lewis acid, if FeBr3 is your Lewis acid, it's accepting a pair of electrons from Br2, right? And there it is, that lone pair. FeBr3 is accepting that lone pair, and now you form this complex. Basically, the complex is just now the Fe, because it gained electrons, is now negatively charged. And because the Br lost its lone pair to make a bond to Fe, any atom that loses a lone pair that was originally neutral is now going to become positive, right? Because it lost its electrons to make a bond. So now you have this complex, and then what happens is Br does not like to be positive. At least in this complex, it doesn't want to be, so it's going to try to break this Br-Br bond to then be able to give Br its electrons back, right? Notice now in here, Br has its lone pair. And now you form Br plus, which is coming from the other Br. Now, this is a way more potent electrophile, right? Look at that. Versus Br2, Br plus is way more electrophilic, right? You guys know that the definition of an electrophile is something that wants to accept electrons. It's really positive, right? It wants electrons because it's positive. We know Br2 temporarily has a dipole where one of the Brs is positive and the other one's partial negative. But look at this one. This one's just bare positive, right? So you already know that this is a way better electrophile than Br2. And this is just showing you how a Lewis acid, when you mix it with something like Br2, can make a way more potent electrophile, okay? And that electrophile is going to react with your benzene, okay? And notice that I could have drawn this either one of two ways. I could have drawn the ring reacting with the complex, or I could have drawn it where, here, let me go back to the pen. You could have drawn Br plus instead, right? Because this Br plus is basically that one right there, right? This is not a mechanism error. I'm just showing you that that Br plus is that Br right over there. But bottom line is that the ring is going to be a nucleophile, right? One of the double bonds of the aromatic ring is going to be a nucleophile, like an alkene can be a nucleophile, right? One of those double bonds is going to do that, and it's going to attack a Br, and you're going to have FeBr4 leave, right? Now what happens is you form, let me go back to the laser pointer, you form something called a sigma complex, which is just basically a fancy way of saying that you form a carbocation on something that was an aromatic ring before. Another way to phrase this is something called an arenium ion, okay? Basically, again, just a carbocation that's part of an arene, okay? But you guys can see that that carbocation is resonance stabilized, right? And notice that you see all these resonance structures. So this sigma complex is stabilized through resonance, okay? And the whole point of this is now you've lost aromaticity in this process, right? This is not aromatic anymore. You started with something aromatic. You lost aromaticity as a result of one of the double bonds acting as a nucleophile to this really, really, really potent electrophile, right? This is so electrophilic that the benzene was like, you know what? This thing is so electrophilic, I'm just going to have to be a nucleophile. Even though I'm going to break my aromaticity, I'm going to break my stability, it's worth it because of how electrophilic this is. It's so powerful of an electrophile that the benzene has no problem losing its aromaticity to behave as a nucleophile, okay? And it does that knowing that it costs some energy to do that, okay? It definitely costs energy to break aromaticity to form the sigma complex. But the good news is that that energy that was lost to break aromaticity is now going to be basically regenerated, right? The aromatic ring is going to be regenerated by grabbing a proton that was there, right? Isn't this proton right here, right? And isn't the whole point of an electrophilic aromatic substitution, EAS, is that you're replacing a proton with an electrophile, your Br, right? And what's going to happen is the FeBr4, which was basically generated in the previous step, is now going to grab that proton, move the electrons where this carbocation is, and notice now you've restored aromaticity, okay? And you got your product. And the byproducts of this are your Lewis acid catalyst, right? You regenerated your catalyst. You started with FeBr3 before, right? Let's just go back a slide. There was your FeBr3. That was your Lewis acid catalyst. And you form HBr, okay? We don't worry about the byproducts, really. We just worry about, okay, we finally formed our product here, okay? So this is a two-step mechanism, guys, of an EAS reaction, electrophilic aromatic substitution. The first step is the aromatic ring performs a nucleophilic attack on the electrophilic bromine complex, the Br+, resulting in a positively charged resonance-stabilized intermediate, which is the sigma complex, and then step 2 is deprotonation, right? Deprotonation of the sigma complex restores aromaticity, and you regenerate your catalyst, and you form your product. Okay? So that's basically how this works. Now we're able to see how we can add different groups through EAS on an aromatic ring. Okay? Now, as I said before, let me go back to the laser pointer. As I said before, there's an input of energy that's required to lose aromaticity, right? And this is why we don't get an addition product. If we got an addition product instead of a substitution product, you permanently lose aromaticity. And notice that you end up way higher in energy than when you started with, right? What's the starting molecule here? Let me just draw that. The starting molecule is just benzene, right? And you got some Br2. And what's happening is, if you get your addition product, you're permanently losing aromaticity. Notice that this product is higher in energy than what you started with, which is not thermodynamically favorable. So this isn't even going to happen. This is not observed. Okay? But the substitution product restores aromaticity, right? We got the aromaticity back from doing the substitution reaction we just saw in the previous slide. And therefore, because you've restored aromaticity, this product is lower in energy than what you started with, which is thermodynamically favorable. Okay? So this is definitely going to happen. This is why we don't observe an addition product, okay? But we do need to enhance the electrophilicity of your Br2 by throwing in a Lewis acid catalyst, which in this case is going to be FeBr3. Okay? All right. So, we can do other electrophilic aromatic substitutions with different Lewis acid catalysts. So we just saw FeBr3 as an example. You can also use AlBr3, which is aluminum tribromide, right? So this is iron tribromide. This Lewis acid is aluminum tribromide. Really, you can use different Lewis acid catalysts to accomplish the same transformation. But realize the mechanism of bromination of an aromatic ring would be the same as when FeBr3 is used. It's all the same. Okay, so if you're wondering what the mechanism is, it's exactly the same as with FeBr3. You can also use AlCl3, and if you do AlCl3, you're going to use Cl2 to now not get a Br on this position, right, where there was a proton. Instead, you're going to get a Cl substituting that proton. Okay? So you could do bromination, chlorination of benzene. Notice that I wrote over here that F2 and I2 does not work well. We've seen the trend with that fluorination is just too violent to be practical, and iodination is just too slow, right? We saw that with like radical reactions way back in Orgo 2, that usually F2 and I2 don't work so great. Br2 and Cl2, though, will work fantastic for this EAS reaction. So, just to take note that the mechanism is pretty much the same as the FeBr3, right? With the AlCl3, you're forming a chloronium ion, right? A Cl+, that is now super electrophilic for the benzene to behave as a nucleophile. You form a sigma complex, which is resonance stabilized. And then you have a proton transfer where you deprotonate this proton to restore aromaticity, and you get your product. Okay? So a really simple two-step mechanism. And I hope you realize a trend here in that all electrophilic aromatic substitution, EAS mechanisms, follow the same two steps. Nucleophilic attack of the benzene. Here, I think I have it on the next slide here. Yeah. Nucleophilic attack of the aromatic benzene on the electrophile. We just call it E for electrophile. That electrophile, once it's added on, is going to be resonance stabilized through the sigma complex. It's just a fancy way of saying you have a resonance stabilized carbocation on an arene. And then through resonance, you guys can see that this proton eventually can be deprotonated and you restore aromaticity, right? So the same two steps throughout this entire process. Now, I do want to point out that you do not have to draw the resonance structures to eventually do the deprotonation. You could just do the deprotonation right away. As soon as you form the carbocation, I could have just drew this here. I could have just shown B for base taking this proton and restoring aromaticity, right? You don't have to draw the resonance. You don't have to do that, okay? Notice that with these arrows, it's accomplishing the same thing. You're still making this product, okay? The double bonds might be in different places, but you guys know that that doesn't matter. In an aromatic ring, you can have the double bonds delocalized within that conjugated system, okay? All right, here's another reaction, another electrophilic aromatic substitution, EAS reaction. This one's called sulfonation. You can guess that sulfonation has to do with sulfur, some sort of sulfur source. In this case, it's SO3. So sulfonation occurs using SO3, which is just sulfur trioxide, as the electrophile. Okay, so SO3 is the electrophile, and you use sulfuric acid as an acid catalyst. Basically, what's happening is you're substituting this proton, just like any other EAS mechanism, this one right here, with an SO3H. Okay? And why is it that we're saying that there's, here, let me go back to the pen here. Why are we saying that there's fuming H2SO4? Why do we call it fuming? Well, fuming H2SO4, it turns out it contains SO3 as a gas. Okay? Here's the Lewis structure of SO3. And why is SO3 an electrophile? If you look at the electrostatic potential map of this, you can see that the blue area, you guys know that the blue means electron poor and red regions of a map mean electron rich, right? So the sulfur you can see is electron poor. And you're probably wondering why. Why is it electron poor? Well, for one, you guys know that oxygen's more electronegative than sulfur. So if you can draw a dipole, you got dipole arrows where the electrons are more towards the oxygen, making these oxygens partial negative, and the sulfur is partial positive, right? Which explains why the sulfur is electron poor. It's partial positive. Also, another reason to explain why it's called fuming H2SO4 is because the SO3 gas reacts with the moisture in the air to produce fumes, and those fumes are basically an aerosol form of concentrated H2SO4. Okay. You could just write SO3 and H2SO4. That's another way of doing it. If you just wrote this is perfectly acceptable. Instead of fuming H2SO4, if you just wrote SO3 and H2SO4, that's also acceptable. And I think in most other texts, you may actually see it just written that way. This is just a fancy way of writing it. But let's go back to asking ourselves this question of why is sulfur electrophilic? Why is SO3 electrophilic? We know the sulfur is partial positive, but an even more in-depth explanation as to why the sulfur is positive is because hopefully you remember this, that any double bond is an overlap of p orbitals, right? You guys know that any double bond is an overlap of p orbitals. Like a carbon-carbon double bond is an overlap of two 2p orbitals, right? But a sulfur-oxygen double bond is an overlap of p orbitals, but the p orbitals are different sizes, right? Why are they different sizes? Because an oxygen exists on the second row of the periodic table, so there's a 2p orbital, and a sulfur atom is in the third row of the periodic table. It contains 3p orbitals, okay? So a 3p orbital is larger than a 2p orbital. They have different sizes, so the overlap between the orbitals is not that great, right? One's larger than the other. And because of that, the SO bond is actually more single bond character than it is double bond character. And because it's more single bond character, it actually is that from a bond polarity standpoint, more of the electron density is concentrated on the oxygen than it is on the sulfur. For the reasons I just described earlier, right? One atom is more electronegative than the other, right? Oxygen is more electronegative. So this is just enhancing our explanation of why sulfur is so electrophilic. Okay? And you guys know the only way a benzene is going to react with an electrophile is if the electrophile is really electrophilic, right? Like so electrophilic that the benzene aromatic ring has no choice but to react with such a potent, strong electrophile. Okay? A regular electrophile is just not going to cut it. And you guys can guess it, right? The mechanism is almost exactly the same, right? This time your electrophile is different, but your benzene's the same, right? Your benzene is going to act as a nucleophile, attack the partial positive sulfur. We just talked about why the sulfur is positive. It's electrophilic. The electrons are going to bounce up to the oxygen, and now you form your sigma complex, okay? Where, again, this carbocation that you formed is resonance stabilized, and eventually water from sulfuric acid is going to pick up a proton because water could act as a base. We've seen that before. To restore aromaticity, and you get your product. Notice there's an additional proton transfer to neutralize that negative charge to make it an OH group. So there is an additional step here. Like I said, electrophilic aromatic substitution reactions have a generic two-step mechanism, nucleophilic attack and then proton transfer. We do have an additional proton transfer just to make that O negative that was made over here an OH, right? And the way that we wrote this out earlier in the previous slide was like this. Right? And now you know where that H comes from. That H is that H. Right? So that's pretty much it for sulfonation. Now, the thing about this reaction, and this is actually really useful, we're going to see why this is so useful. This reaction is useful because when you do the sulfonation, this is actually a reversible process. So if you dilute this reaction, meaning you just add more water to it, you don't make it as concentrated, it goes back to having the proton here. And we don't really need to discuss the mechanism for that. Just know that this is a reversible process. We could get into the mechanism. It's not that bad, but for the sake of time, I'm just not even going to worry about that. And it's not like you need to worry about it for any sort of standardized exams like the ACS, MCAT, or DAT. You just need to know that this is a reversible reaction. Okay. Okay, another type of electrophilic aromatic substitution reaction is nitrations. Okay, so like sulfonations, nitrations are replacing a proton, right, with an NO2. Okay, that's why it's called nitration, because you're adding an NO2 group, right? A nitro group is an NO2 group. You guys remember that? Now, nitration occurs when you have HNO3 as the source of the electrophile, okay, and H2SO4 as an acid catalyst. Kind of like sulfonation, where H2SO4 is also an acid catalyst. For nitrations, it's the same thing. But the source of the electrophile is HNO3, okay? And it's believed that the nitronium ion, NO2+, is the active electrophile, right? Notice that in every electrophile we've seen so far, almost all of them have some partial positive, really strong partial positive character, or just positive character, period. You guys know anything that's positively charged is a great electrophile, right? It's so good that anything that is debating to be a nucleophile is going to be a nucleophile towards stuff like this. But how do you make NO2+ from HNO3? Like, where does the NO2+ come from? Because we don't see it in our reagents, but we do make this from mixing HNO3 and H2SO4 together. Let's take a look. So NO2 is the active electrophile, NO2 plus. Now, how do we make NO2 plus? So basically, there's an acid-base reaction between HNO3 and H2SO4, okay? And I know that's weird because these are both acids, right? Nitric acid and sulfuric acid. So how do you have an acid-base reaction with two acids? Well, you guys know that acidity is relative, right? Like one acid is stronger than the other, right? So the stronger acid is going to be the better acid, and then the one that's weaker between the two is going to be a base, okay? Which I know sounds weird, but it makes sense from a pKa standpoint why this would happen. And it turns out that nitric acid is less acidic than sulfuric acid. So what's going to happen? This is the Lewis structure of HNO3, okay? You guys know how to draw Lewis structures at this point. If you don't remember how to do that, I recommend reviewing that. It's not that important, but I mean, you should know how to draw Lewis structures. Specifically for nitric acid, that's an important one. Sulfuric acid too. But basically what's happening is the HNO3 is going to behave as a base, take a proton from H2SO4, right? You form this intermediate that then collapses by having water as a leaving group. And when water leaves, this is aided by having a lone pair on one of the oxygens, a negatively charged oxygen, to come back down, form a double bond, and kick off water. And now you form this nitronium ion, where the nitrogen has two NO double bonds, and because this nitrogen has 4 bonds to it, it's going to have a positive charge. That positively charged nitrogen is super electrophilic. This is the active electrophile, okay? And you guys can guess it. Once this sees benzene, let's take a look. Once this sees benzene, it's just going to do a nucleophilic attack on that nitrogen, electrophilic nitrogen. And the electrons are going to come up to the oxygen as a result of that to make a neutral nitrogen. And now you formed your carbocation on your arene ring to form a sigma complex that is resonance stabilized. We already saw this, right? There is water hanging around in sulfuric acid, right? Because it's concentrated sulfuric acid, concentrated nitric acid, all has some water in it. That water can behave as a base to deprotonate the proton on the arene to restore aromaticity. Okay, and now you get your product. Same two-step mechanism, right? For all EAS reactions. What's the only difference? The difference is the electrophile. That's it, right? So we just saw that we have NO2 as an electrophile, Br plus, Cl plus. What else did we see? SO3 was a good electrophile, right? So again, I'm just showing you all these different classes of EAS reactions. Now, the other thing that you need to take note of is when you get the nitro group on a benzene and you perform a nitration, you can actually reduce this NO2 down to an NH2. And you're probably wondering, why do we care about that? Why do we want to reduce this? You guys will see in a little bit why this is an important reaction. Right now, I'm not really stating much the importance of these reactions, but you'll see once we start substituting the benzene even more, right? Let's say we want like more groups on the benzene. Eventually, you're going to see why we want this to be an NH2 rather than an NO2, okay? It helps substitute the ring at different positions. It's just foreshadowing some future concepts. But bottom line is, if you want to reduce this NO2 to NH2, you need to use iron or zinc with some HCl, okay? And you're wondering, how is that happening? What's the mechanism or something like that? Honestly, we don't need to worry about the mechanism for this. Usually anything metal related is a little more complicated mechanism-wise, but we're not going to worry about how iron and zinc is actually doing this. But just know that when you use one of these two metals with HCl, you're going to reduce this NO2 to an NH2, okay? Now, why do we need NaOH hydroxide as a second step to do this? Well, you guys know that if you form this product, let me go back to my pen. If you form this product and you have HCl hanging around, you guys know nitrogen's basic enough to take the H from HCl. So what's going to happen is you're going to have NH3 plus hanging around. But we don't want NH3 plus as a product. We want NH2. So that's why we need this base. So that base, NaOH, can take that proton back, right, and make the NH2 again. Right, so all I'm really saying here is that you need sodium hydroxide to remove the extra proton and regenerate this amino group, right? This is an amine. So you went from a nitro to an amine. Now, when you combine these reactions, you get this overall process. Okay? The first step is nitration, followed by reduction of that nitro group to an amino group. Okay? 3-step process. Okay, so this slide is asking to draw a mechanism for the following reaction. This is just a practice problem. And it says make sure to draw all 3 resonance structures of the sigma complex. I mean, we could do that. Honestly, you guys saw that we don't need to do that. I'm not going to do that. But what I do want to show here is at least the important part of the mechanism. I'm just going to draw the Lewis structure for HNO3. Okay, that's HNO3. And you know that, hopefully you guys can draw the Lewis structure for H2SO4. It's not that bad. There it is, right? I'm not including the lone pairs here. We don't have to. Really, the only lone pairs that are important, which are these. All right, so that's the first step. Remember, we said earlier that nitric acid is not as acidic as sulfuric acid. So the nitric acid is therefore going to behave as a base towards sulfuric acid, generate water. And now the lone pair on this oxygen is going to come back down, kick off the water, and you now form your nitronium ion, which is nitronium ion, super electrophilic, right? And now let's get the benzene ring involved, because we have our electrophile. It's super pumped up to react with really anything on site. In this case, benzene. Well, not benzene, but tetra-substituted benzene, right? Tetramethyl. Doesn't really matter, because right now, I'm just going to draw the active electrophile. This is going to attack. Benzene is going to be a nucleophile, attack, and now you form your positive charge right over there. Oh, forgot that these electrons need to come over here. Right, and remember there's a proton here. I'm not going to draw all the resonance structures for that carbocation. We could do that. I know the question asked for it. For the sake of time, I'm not going to do that. I'm just going to have water come in and restore the aromaticity, because we just lost aromaticity from the attack. Reforming aromaticity. Just going to label this NO2, right, because this is a nitro group, right, NO2, with the 4 methyl groups that are still there. And there's your product. Now, you're probably wondering, why didn't the NO2 go on the other carbon? Well, notice we formed a way more stable carbocation. This is a tertiary carbocation, right? Versus if I did the attack on the other one, you wouldn't get a tertiary carbocation, right? If I went this way instead, if I did that instead, then the carbocation would go there, right? And that's not a tertiary carbocation, that would be secondary. So notice that in this mechanism, I really paid attention to where the NO2 is going. And that's going to be more important going later as why that NO2 is ending up at that position. But right now, we just saw that this sigma complex is more stable with a tertiary carbocation than if it was secondary, right? So hopefully that makes sense. That's just an example of an electrophilic aromatic substitution reaction, specifically nitration. Okay. All right, here's another class of reactions called Friedel-Crafts alkylation. Friedel-Crafts alkylation. So this is just another type of EAS reaction. Okay. Now, within the realm of EAS reactions that we just talked about, we talked about nitration, sulfonation, chlorination, bromination of a benzene, right? All the electrophiles were Br plus, Cl plus, some positively charged, really active electrophile, right? NO2 plus. SO3 is not plus, but that sulfur is pretty partial positive, right? We saw that. But now let's explore electrophiles where the electrophilic center is a carbon atom. Can we do an electrophilic aromatic substitution reaction where the electrophile is a carbon atom, right? The electrophilic center. And the answer to that is yes, we can. It's called a Friedel-Crafts alkylation. So if you're alkylating, you guys know what alkylation is. It's when you're adding some sort of alkyl group, a carbon group, hydrogen-based group. And usually we do that with some sort of alkyl halide, right? The alkyl halide as an electrophile, you've seen that before with like substitution reactions and stuff like that. But we need to amp this up a little bit because it's like we said, an alkyl halide, it's a good electrophile, but it's not electrophilic enough, right? Not electrophilic enough to react with benzene. It just won't do it. You need to tickle it with a little bit of Lewis acid catalyst like aluminum trichloride, okay? Aluminum trichloride is going to get this process to go. Excuse me. So how is aluminum trichloride going to get this to be more electrophilic? Because right now this is an okay electrophile, but we can make it better using some Lewis acid catalyst like we saw before. Well, the mechanism is exactly the same. Right? Remember when we had, here, let me go back to my pen here. Remember when we had like Br, or Cl, right? What was the first step? Cl attacked the aluminum, and then you generated the complex, and then you formed Cl plus, right? Well, instead of Br, Cl, now you have the Cl from your alkyl halide attacking your aluminum, and you form this complex, and then this complex breaks apart by giving the chlorine its electrons back. Remember, chlorine doesn't like to be positive. It's going to try to not be. And as a result, you now form a carbocation. And you guys know carbocations are super electrophilic, right? I mean, there's a positive charge on that carbon. There's a nucleophile around that would like to react with this, and that's going to be the benzene. And just to show you what that looks like, now that you've generated your carbocation from your alkyl halide, facilitated by the Lewis acid catalyst, you now are going to have your benzene behave as a nucleophile. Same process, right? Same thing, where you now form your sigma complex, you restore aromaticity, right? Notice that the aluminum tetrachloride now that was generated from the previous step, right over here, right? This aluminum tetrachloride that's hanging around is going to help restore aromaticity by grabbing this proton. You now have your alkyl group added in with your byproducts. Okay? So Here's another example of an EAS reaction, and this time we've added an alkyl group, right? Before we replaced this proton with a bromine, a chlorine, a nitro group, a sulfonyl group. Now we've added an alkyl group, okay? Now, just to make a note of this, that primary halides can also happen with primary halides, right? Notice that the carbocation we formed before was a secondary carbocation. You can get this to happen with instead of a secondary alkyl halide, you can get this to happen with a primary alkyl halide. Okay, you can accomplish the same reaction, except the one thing is that we don't actually generate primary carbocations in solution. They're way too unstable, right? You guys know primary carbocations are not going to happen. Instead, the electrophilic agent is the complex itself, right? With the secondary substrate, we actually had the carbocation as, separated from this complex because we don't mind generating secondary carbocations, but with primary substrates, it just stays this complex. It doesn't do this. It doesn't do this. The chlorine's not going to get those electrons back, right? You're not going to make, this carbon-carbon with its hydrogens. You're not going to make this primary carbocation. It's just not going to happen. It's just too unstable. So the active electrophilic agent is just this complex, okay? But the mechanism is all the same. It's really not that different. Now, there's a bit of a problem with alkylations, right? Like, it's great that we can put alkyl groups on benzene. Like, we can actually add groups to the aromatic system and regenerate aromaticity, restore it. That's all great. But the problem is that most primary alkyl halides, you guys know, are susceptible to rearrangement because we know we don't like primary carbocations, right? Oops. If a primary carbocation could rearrange to a better carbocation, it'll do it, okay? And here I'm just showing a situation where you have a primary alkyl halide that can basically rearrange to a secondary carbocation. Now, this may not seem as obvious. Let me draw this in another way so you understand what's going on. Let's just say, forget about this arrow for a second. Just forget about that. Just imagine right now that this arrow is happening. And when that arrow is happening, you form that, right? But you guys know that's a primary carbocation, which through a hydride shift, that's where this arrow is coming in. With a hydride shift, you can make a secondary carbocation, which is way more stable than a primary carbocation. But this poses a problem, because if you're trying to get this right over here, this primary carbocation, to add to a benzene ring and make that product, it's not going to work so great, because before this even happens, you're going to generate the secondary carbocation and make this product. So now you have a mixture of products that's basically unavoidable. And you guys know that when we have chemical reactions, we don't like making more than one product. We prefer making selectively one thing and not having a mixture. I mean, having a mixture of products is really annoying to deal with. If you're in a laboratory setting and you're trying to make one thing and you're making a mixture, that's not any fun, because now you have to figure out how to separate the compounds from each other, purify them. And between these two, to purify these two, that is a pain. It's just better to try to make one product. So this is unavoidable. I mean, you're getting a mixture of products, and really this just comes to show that Friedel-Crafts alkylation reactions are only useful when the substrate that you're dealing with, the alkyl halide, is not going to be susceptible to a rearrangement. It's not going to undergo a rearrangement. That's the only time Friedel-Crafts alkylations are actually good and useful. But when you're dealing with an alkyl halide that is going to undergo a rearrangement, you're inevitably going to make a mixture of products. Um, Now, there's a way to fix that. We're going to see that in just a second. But a couple other things I do want to mention is that there are some other limitations to Frito Craft's alkylations. One of the other ones is that the halide leaving group should be attached to an sp3 hybridized carbon, right? You can't have this alkyl halide that's sp2 hybridized, sp2, right? Because you can't make carbocations on sp2 centers. They're just not stable at all for Frito Craft's conditions. Just won't work. So that's a limitation with Frito Crafts, right? We just saw the other limitation before, that you can get rearranged products. This one is just the limitation on the types of alkyl halides you can use. The other limitation is that you can get polyalkylation. So what that means is if you do one alkylation, you're susceptible to do another alkylation. And you're probably wondering, why did the second alkyl group end up on opposite side of the ring? Why did it not end up like here or there? We're going to talk about all of that in another video. But just know that the issue with Frito Craft's alkylation is you get multiple products. The last limitation with Frito Craft's alkylations is when you have something like nitrobenzene and you're trying to do an alkylation, it's just not going to work. And the reason why is because nitrobenzene is just too deactivated to react. And you're probably wondering, what does that even mean? What does it mean for something to be deactivated? Again, we're going to talk about that in another video, what it means when something's deactivated and why nitrobenzene is responsible for deactivating this ring for this reaction. We're going to learn that in another video, so don't worry. But right now, just know that alkylations will not work with aromatic rings that have a nitro group on it. Okay, so let's wrap this up with some practice problems. It says, predict the expected products when benzene is treated with each of the following alkyl halides in the presence of AlCl3. In each case, assume conditions have been controlled to favor monoalkylation. So you're not going to get multiple alkylation products. Let's go back to the pen. So I put this together on a problem set. You'll be able to practice these on your own, but let's just do one of these. Let's just do A. Okay, so the question said that you're starting with benzene and it's treated with an alkyl halide, which is in this case that with some aluminum trichloride. So what is the product that you're going to get? Now, when you're doing this, what I would do is I would generate the active electrophile when you mix both of these together. When you mix both of these together, your active electrophile is going to be your carbocation where the Cl was, right? And that is where you're going to now say, hey, I'm going to have my benzene react. And now you, oops. You now generate carbocation there. You guys know that you're going to regenerate your Lewis acid catalyst, restore aromaticity. And get your product. Now, keep in mind that before you do all of this, you need to ask yourself, is this electrophile, this active carbocation electrophile, is it going to rearrange? And you can guess it. It's not going to rearrange. Even if it did, it's going to end up being the same thing anyway, right? Just because the carbocation is here versus over here versus over there versus over here versus over here, it doesn't matter, right? This carbocation has no tendency to rearrange. And therefore, you're going to exclusively get this product. You're not going to get any rearranged products from this, okay? Now, you can try B and C and ask yourself, whenever you're making a carbocation, hopefully you realize the trend that what's the active electrophile for this one, for part C? It's going to be this, right? When the leaving group leaves. Now, just by looking at that, you already know that's a primary carbocation. That is definitely going to rearrange, right? And you guys can see that there's a hydrogen right there. There'll be a hydride shift where you're going to make a tertiary carbocation. And you can guess it that with C, you're going to get a mixture of rearranged products, right? With B, that's not going to happen because you already form a nice tertiary carbocation. So those are just some practice problems related to this, right? Realize that in a lot of cases, Friedel-Crafts alkylation's all not that great because you're going to get rearranged products. Now, there's a way to counter this problem. There's a way to fix this, okay? How do you fix rearranged products? Well, what if instead of an alkylation, you do an acylation? You guys remember what an acyl group is, right? That's an acyl group. We talked about that before. Just like you can add an alkyl group to a benzene, you can also add acyl groups to a benzene. And you're going to see just in just a second why this is so great to do, because you're going to this is going to solve the problem of rearranged products. But right now we need to discuss how can we add an acyl group to a benzene. Well, just like really anything else, you need a Lewis acid catalyst like AlCl3, and you need an acyl chloride, right? Like an alkyl chloride or an alkyl halide, you need an acyl halide to be able to do this, right? So you guys can see the similarities here, that if you want to add an alkyl group, you start with RCl, right? Like an alkyl chloride, or it could be any sort of halogen, RX, right? With this, you need to start with an acyl halide, right? Or really any sort of acyl halide here, okay? So that's how you do that. And what's the mechanism for this process? It's pretty simple. And it's really not that much different than all the other EAS reactions you've seen. The active electrophile is something called an acylium ion. Acylium ion. What the hell is that? Well, you guys saw that whenever you use a Lewis acid, it needs to accept electrons, right? It's accepting electrons from the Cl, right? That's not surprising. We already saw that 1,000 times. And when that happens, you generate a Cl plus that then says, hey, I want my electrons back. Cl is like, I don't like to be positive. I want those electrons back. I know I gave up my electrons to go to the Lewis acid, become positive, but I want those electrons back, and I'm going to get it back from this bond, right? But when that happens, you form this acylium ion, right? Where now this carbon became positively charged because it lost those bonding electrons, right, to go to the Cl. And this is called an acylium ion. Now, what's nice about this ion relative to a carbocation that we saw before, this one is resonance stabilized, right? Notice that you can draw a resonance structure of this acylium ion. These are the same thing, right? And because they're the same thing, you can see now this lone pair can be delocalized to form this resonance structure. And this resonance structure is actually the more significant resonance structure because all the atoms have an octet, okay? So this is the active electrophile. And this is nice because once you have a full octet between the two atoms, there's really no reason for any sort of rearrangement. right? This is not going to undergo a rearrangement. You can imagine if this R group was some other carbons, there's no reason for that carbocation that's resonance stabilized to do any sort of rearrangement. So the stability of this resonance structure allows for this to just react with no rearrangement. And you guys can guess it that as soon as you have your active acylium ion electrophile, your nucleophile is going to be the benzene. It's going to attack this electrophilic carbon, send the electrons back up to oxygen. Why? Because it's dying to get those electrons back. You guys know oxygen does not like to be positive. So to get that oxygen to become neutral again, this carbon is accepting a pair of electrons. One of the pi bonds breaks to go back to the oxygen. And now you form a sigma complex with your acyl group attached to your, what was your arene, but now your arenium ion. This is resonance stabilized, and you guys can guess it. You know, at this point, you just use aluminum tetrachloride to remove this proton and regenerate aromaticity. And now you get your acyl group on your benzene. So there's your Friedel-Crafts acylation mechanism, which again is very similar to all the other mechanisms you've seen for electrophilic aromatic substitution. Now, why is this such a great reaction relative to alkylation? Because now you can reduce this carbonyl down all the way to just have 2 H's. Now, you've learned a couple of ways to do that. You learn how to do that with Wolff-Kishner, right? Where you convert a carbonyl to 2 H's. You could do that through Wolff-Kishner. You can do that with the thioacetal and ranitidine, right? That's another way to do this. And then there's another way to do this. It's called a Clemmensen reduction. We haven't really talked about that before, but it's another way. This is basically a third way to do this in your toolbox of going from a carbonyl, reducing it all the way down to the alkane. And you do that with some zinc amalgam, which is just amalgamated zinc. It's an alloy of zinc and mercury with some HCl and heat. I've seen people just use zinc and HCl to do this as well. That works. You don't need amalgamated zinc. You could just do this with zinc HCl, which we've used before to reduce the nitro group to an amino group, remember? You can do this to now get this down to the alkane. Now, was it possible to make this product before? No. Because if you try to make this product with, I'm just going to draw the alkyl chain that's added on here. It's 4 carbons, right? 1, 2, 3, 4. 1, 2, 3, 4. If you started with the alkyl halide, let's just put a chloride there. You guys know that if I just use this and not this, I'm going to generate a primary carbocation as my active electrophile. And didn't we just say that primary carbocations are susceptible to rearrangement? Which means you're going to get a mixture of products. You're not going to get just this. But with the acylation, you prevent and avoid the rearrangement from happening in the first place. And if that happens, you generate just this product, right? This product right here, that you can then reduce down to get this, and exclusively this, only this. So this is a nice way to get an alkylated product that avoids a mixture, right? You're just going to get this one. So to be honest, most of the time you're going to use Friedel-Crafts acylation to install alkyl groups because you avoid the concept and possibility of rearrangement. This is why this is so useful. Here's another reason why it's useful, because now you're not going to get polyacylation, which was a problem with alkylation. Remember how we said with alkylation you get more than one alkylated product, right? Like you get more of this on there, and this is not going to happen with acylation. This acyl group is deactivating this ring from doing any other nucleophilic reactions, and Again, I use the term deactivating. I want to talk about what that means in another video, but that's not going to happen here. Okay, let's wrap this video up with some practice problems related to Friedel-Crafts alkylation. It says identify whether each of the following compounds can be made using a direct Friedel-Crafts alkylation or whether it is necessary to perform a Friedel-Crafts acylation followed by a Clemmensen reduction to avoid carbocation rearrangements. Okay, so let's just do A. So when we're thinking about that, what we need to do is we should draw what the active electrophile to that benzene is going to be. And you guys can see that I'm adding this group. So let me just draw that group. Right, and if you're wondering, like, how did I get that? How many carbons is this? This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you see that the bond that's being made is right over here, right? So the carbocation had to be on number 5 for the benzene to make a bond to it, right? Now, is this carbocation going to undergo a rearrangement? Well, it definitely can, right? We don't only have hydride shifts, we also have methyl shifts. And one of the methyl groups, number 1, number 2, or number 3, can shift over to number 5. I just picked number 1. So here's number 4, number 2, number 3, and here's number 5. And we just had number 1 attached to number 5. And now where's the carbocation going on number 4? Right? Because number 4 just lost the bond. It was bonded to 1, but it's not. Now 5 is bonded to 1. And 4 missed out on a bond, so it gets a carbocation, right? And look at that. You got a tertiary carbocation. That's way better. So what does that mean? That means you can't do this reaction with Friedel-Crafts alkylation. You need to do this with Friedel-Crafts acylation. Okay? And what would that look like? Well, if you have a benzene and you need to add this group, I'm just going to draw the group. Right? 1, 2, 3, 4, 5. And on carbon 5, instead of a chloride, it's going to be an acyl group with a chloride. And you need a Lewis acid aluminum trichloride. And you're going to get this product. Can't do this with alkylation, guys. You cannot use this alkyl halide as the electrophile because you know this is going to make this, which is then going to make that and rearrange, and you're going to get a mixture of products. All right, so that's just an example problem. You can do the other 3, B, C, and D. Try those out with the logic I just used for problem A to figure out whether you need to do those with Friedel-Crafts alkylation or acylation. Which one's better? All right. You can say that all of them can be done through acylation because you avoid that problem, but there are some of these on here that you can just do an alkylation and it'll be perfectly fine. Okay. All right, last one. I know we're about an hour in the video. Let's just do this last practice problem. It says the following compound cannot be made with either a Friedel-Crafts alkylation or acylation. Explain. Okay. Why can't it go through either one? Well, if I break this up, I know that benzene needs to react with this group, right? I can just number the carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, with alkylation, you guys know that at number 5, because that's where the bond's being made, I'm going to have some sort of halide. Let's just put a chloride there at number 5. You guys know that when this leaves eventually, you're going to make this. And that's a secondary carbocation right now that could rearrange to form a tertiary carbocation, right? You could do like a methyl shift like that, and it can become tertiary, right? So the problem is that you can't make this compound through an alkylation because it's going to undergo rearrangement, right? And you're going to get a mixture. But why can't you do acylation? Because that should solve the problem, right? Well, remember, for an acylation, you need a double bond O on carbon number 5, right? But you also need a Cl, right? Like some sort of halogen coming off, right? And you can't add a halogen on carbon 5 because carbon 5 already has 4 bonds. You can't just add a 5th bond, right? So there's no way you can make the acyl chloride from this. That's why this is a really difficult product to make. And you can't make it through alkylation or acylation. So you pose a problem there, and that means you have to figure out another way to make this molecule synthetically. Not that we need to go into that, but we just saw that there is a small limitation here, that you can't always get any alkylated product you want on a benzene, right? You do have some limitations. Okay, with that, that pretty much wraps up video 1. I'm going to go into video 2 talking about the other concepts I foreshadowed with like the deactivating, activating stuff. So stay tuned for video 2 related to aromatic substitution reactions. Thank you.